Welcome, everyone, to Grade 9 Science, Term 1, Week 4. Today we begin a brand new unit, electricity, current, voltage, and resistance. Over the next few days, we're going to find out what electricity really is, how a simple circuit works, and how voltage, current, and resistance relate to one another through a rule called Ohm's law. By the end of this lesson, you'll be able to explain electricity in your own words, and even solve real problems using the formulas we'll learn together. Let's get started. Before we dive in, let's look at what we're aiming to learn today. First, we will describe the nature of electricity, what it actually is at its most basic level. Second, we will enumerate the different components, or parts, of a simple circuit. And third, we will relate electric current to voltage and resistance. Keep these three goals in mind as we go along. By the end of this lesson, you should be able to check off all three. Let's start with something we all experience every single day. Every night, the lights in our barangay turn on. Our television, our rice cooker, and our cell phone charger all work, and all of this happens because of electricity. But here's a question worth thinking about: what is electricity, really? Have you ever experienced a brownout, a power interruption? What happened to your appliances when the power went out? Take a moment to think about your own experience, because that everyday knowledge is exactly where our lesson begins. Before we go further, let's check some important vocabulary we'll be using throughout this lesson. An electric circuit is a closed loop through which electric charges can continuously move. Electric current is the rate at which charge flows past a point in a circuit. A series circuit has only one pathway for charge to travel. A parallel circuit has two or more pathways for charge to travel. And resistance is the hindrance or opposition to the flow of charge. Try writing your own definition for each of these terms first, then compare it with what's on the screen. This will help activate what you already learned back in elementary science. Let's begin subtopic 1, the nature of electricity. Our guiding question for today is this: where does electricity come from, at the smallest level? To answer that, we're going to look inside the atom itself. Every atom is made up of three types of particles. The proton carries a positive charge, and it stays inside the nucleus, at the center of the atom. The neutron has a neutral charge, meaning it carries no charge at all, and it also stays inside the nucleus. The electron carries a negative charge, and unlike the proton and neutron, it moves around the nucleus. It's the electron that we care about most in this lesson, because electrons are the particles responsible for electric current. Now that we know electrons move around the nucleus, let's connect that to electric current. Electrons are responsible for electric current, and charges can flow when voltage is applied. In simple terms, current is charge in motion, the flow of charge. We describe this using the formula I equals Q over T. Here, I stands for current, measured in amperes, Q stands for charge, measured in coulombs, and T stands for time, measured in seconds. Keep in mind that the charge of just one electron is incredibly tiny, about -1/602 times 10 to the -19th power coulombs. That's why, when we talk about everyday electric current, we're really talking about the movement of enormous numbers of electrons all at once. Let's put our formula to work with an example. The question is, how much current is in the wire if 500 coulombs of charge flows for 10 minutes? Step 1, we identify what's given. Q equals 500 coulombs, and T equals 10 minutes. Step 2, since our formula needs time in seconds, we convert. 10 minutes times 60 seconds per minute gives us 600 seconds. Step 3, we apply the formula, I equals Q over T, so I equals 500 coulombs divided by 600 seconds. Step 4, solving that gives us our answer. I equals 0.833 amperes. Or, written another way, 833 milliamperes. Notice that we always convert time into seconds first, because the ampere, our standard unit for current, is defined as coulombs per second. Let's try a slightly more advanced example. A steady current of 3.0 amperes flows in a wire for 5 minutes. How much charge passed through, and how many electrons does that represent? First, let's find the charge. We rearrange our formula to get Q equals I times T. So, Q equals 3.0 amperes times 5 minutes converted to seconds, which is 300 seconds. That gives us Q equals 900 coulombs. Now, let's find the number of electrons. We know that one electron carries a charge of 1.602 times 10 to the -19th power coulombs. So, The number of electrons equals 900 coulombs divided by 1.602 times 10 to the negative 19th power coulombs. That works out to approximately 5.62 times 10 to the 21st power electrons. That's an enormous number, and it shows just how many electrons are needed to produce even an ordinary, everyday electric current. Now it's your turn to try one on your own. Here's the question: how much current flows if 350 coulombs of charge passes in 5 minutes? Pause the video, or take about 2 minutes to work this out yourself before checking the answer. Ready? Here's the solution. I equals 350 coulombs divided by 5 minutes converted to seconds, which is 300 seconds. That gives us I equals 1.17 amperes. If you got that answer, well done. You've got a solid grasp of the current formula. Let's move on to subtopic 2, building a simple circuit. Our guiding question today is: what parts do we need to light a bulb? We're moving from theory into a hands-on look at the actual components of an electric circuit. Every simple circuit is made up of 4 essential parts. First, the voltage source, for example, a battery, which pushes the charges through the circuit. Second, connecting wires, the path that the charges travel through. Third, the switch, which opens or closes the pathway, allowing us to turn the circuit on or off. And fourth, the load, for example, a bulb or a resistor, which uses the electrical energy to do something useful, like producing light. All 4 of these parts must be connected in one closed loop, running from the positive terminal of the battery all the way to the negative terminal, for current to flow. Let's compare 2 states a circuit can be in. In an open circuit, there is a gap somewhere in the wire, so charges cannot flow, and the bulb stays off. In a closed circuit, there is no gap at all. Charges can flow all the way around the loop, so the bulb lights up. The key difference is simple. A gap means no current, and a complete loop means current flows freely. To draw circuits clearly, scientists and engineers use standard symbols. A straight line represents an electrical wire. A broken line with a small diagonal lever represents a switch. A circle between 2 wire segments represents a light bulb. 2 parallel lines, one long and one short, marked with a plus and a minus sign, represent a battery. A rectangle between 2 wire segments represents a resistor. Note that a bulb can also be represented using this resistor symbol. And a circle containing a wave symbol represents an AC voltage source. Keep these symbols in mind, because we'll use them to draw and read circuit diagrams. Now it's time to practice. Using the symbols you just learned, convert an actual, physical circuit into its schematic diagram. Here's an example answer. 2 light bulbs connected in series, along with 1 battery and 1 switch, all forming a single closed loop. Try sketching this yourself before comparing it with the example, so you get comfortable translating a real circuit into its symbolic form. Let's move into subtopic 3, Ohm's law. Our guiding question today is: how are voltage, current, and resistance related to one another? To explore this, we'll look at what happens when we adjust voltage and resistance in a circuit simulation. Here's what we typically observe when experimenting with a circuit simulation. When voltage increases, current also increases, and the bulb glows brighter. When resistance increases, current decreases, and the bulb glows dimmer. In other words, current is directly proportional to voltage, meaning they increase and decrease together, and current is inversely proportional to resistance, meaning as one goes up, the other goes down. This relationship is formally known as Ohm's law. The main equation is V equals I times R. From that single equation, we can derive 2 more useful forms. I equals V divided by R, and R equals V divided by I. Here, V stands for voltage, measured in volts, I stands for current, measured in amperes, and R stands for resistance, measured in ohms. A helpful memory trick: picture a triangle with V on top, and I and R on the bottom. Cover the letter you want to solve for with your finger, and whatever remains visible tells you the formula. Covering V leaves I times R, covering I leaves V over R, and covering R leaves V over I. Let's apply Ohm's law to a real, everyday example. A hair dryer draws 9.0 amperes when plugged into a 220-volt line. What is its resistance? Step 1, we identify what's given. V equals 220 volts, and I equals 9.0 amperes. We want to find R. Step 2, we choose the correct form of Ohm's law for resistance, which is R equals V divided by I. Step 3, we substitute our values. R equals 220 volts divided by 9.0 amperes. Solving this gives us our answer. R is approximately 24.4 ohms. So, this hair dryer has a resistance of about 24.4 ohms. Now it's your turn to apply what you've learned. Here are 3 problems to solve. Number 1. A flashlight bulb draws 520 milliamperes from its 9.0 volt battery. Solve for the resistance. Number 2. What is the resistance of an appliance if 220 volts produces a current of 5 amperes? Number 3. How much voltage will produce 0.50 amperes of current through a 1500 ohm resistor? Take a few minutes to work through these on your own or with a partner. Here are the answers. For number 1, the resistance is about 17.31 ohms. For number 2, the resistance is 44 ohms. And for number 3, the voltage is 750 volts. Check your work against these answers and review any step where your answer didn't match. Electricity is incredibly useful, but it must always be handled with care. Let's go over some important safety reminders. Never touch electrical wires or outlets with wet hands. Do not overload a single outlet with too many plugs. This is sometimes called Gaddison here at home. Always turn off the main switch before repairing any wiring. And report any exposed or damaged wires to an adult immediately. These simple habits can prevent serious accidents. So please keep them in mind not just in school, but at home as well. Let's connect everything we've learned into one big picture. At the center of it all is electricity itself. The nature of electricity tells us that electricity is fundamentally the flow of electrons, described by the formula I equals Q over T. Simple circuits tell us that this flow needs a path, made up of a voltage source, wires, a switch, and a load. And Ohm's law tells us how voltage, current, and resistance relate to one another along that path, through the equation V equals I times R. Together, these 3 ideas give us a complete picture of how electricity works. Let's recap the 4 big ideas from today's lesson. First, electricity is the flow of electrons through a circuit. Second, a simple circuit needs a voltage source, wires, a switch, and a load, all connected in one closed loop. Third, Ohm's law tells us that current is directly proportional to voltage and inversely proportional to resistance, expressed as V equals I times R. And fourth, always practice safety when working with electricity. Keep these 4 takeaways in mind as we move into our reflection.